without further ado, I want to introduce James Eastham. Over to you.
I'm sure many of you can relate to that noise, can't you? Probably has some deep-rooted emotional response, doesn't it? For some of you, it's probably anger. Why is my pager going off at this time of day? Maybe for some of you, it's happiness, because you know it's your time to be a hero, right? No, it's definitely the first one, isn't it? To have the laughs. I'm sure you've all been there where you receive a page, you go and try and diagnose the issue, and you can't, for the life of you, work out what is going on. And before you know it, you're command-Fing your way through a giant wall of JSON-formatted logs trying to work out what the heck your system is doing. These things got all the more difficult once you started building distributed systems. Now, instead of a log file on a single machine, you've got lots and lots of machines spread across an entire cloud provider. Maybe you're not even using machines at all. And then you made the excellent decision to make your system event-driven. You read about it online, you saw conference talks, you saw lots of articles, you saw AWS publishing things, and you thought, this must be the only way to build reliable and scalable systems in the cloud. And now you're sat there at 3 o'clock in the morning, wondering why you chose to make this decision. Now you can't understand what is causing your system to do the thing that it's doing. And that's what I'm going to talk to you about in this talk. I'm going to tell you what it is that makes observability so difficult in asynchronous systems, and then hopefully give you some practical things that you can take away and use in your systems. I'm James Eastham. I'm a serverless developer advocate at Datadog, but don't worry, this is not a talk about a specific SaaS product, a specific technology, a specific programming language. This is a talk about observability. Now, for any of you who've heard me talk before, you'll know there's one thing I love to talk about almost as much as event-driven systems, and that is pizza. How many people loves pizza, by the way, just a quick show of hands? Okay, those of you with your hands down, come on, really? So for the rest of this talk, I want you to imagine your page has just gone off, and you're a developer for a fictional pizza delivery company called Plant-Based Pizza. Imagine it's the middle of the afternoon, there's a big sporting event or something on, and lots of people are trying to order pizzas, and your system isn't working. So now you need to figure out, well, why? And to understand that, let's just take a step back and look at the actual architecture of the system you're working with. This is how things started. Things were much simpler then. A single running process, a single database. Things were nice and easy to think about, nice and easy to reason about. And then you started to scale. And of course you're going to scale because your pizzas look like that, right? They look amazing. So eventually you started building distributed microservices. You broke things down into these small pieces of independently deployable functionality, all communicating over synchronous HTTP APIs. This started to give you a lot of pain, though. All your systems were really tightly coupled together. They're communicating over these synchronous interfaces. Now, of course, coupling isn't necessarily a bad thing. If you built a completely decoupled system, it would be really hard to get any meaningful work done. Event-driven systems aren't decoupled, they're simply loosely coupled. And this leads to one of the common rules of thumb in software architecture, that you should aim for loose coupling and high cohesion. Now, cohesion you've already kind of figured out. You're building microservices, the things that change together should live together, and you've got these independent pieces of functionality that are all being deployed independently. Cohesion, though, coupling's a little bit trickier. There's lots of different types of coupling, and you want to try and make this coupling as loose as possible. So that led you to where you are today. This is your high-level architecture today. At very high level, you've got 5 different services, all communicating completely asynchronously, all communicating completely with events. And to just walk through this at a functional level to see exactly how things work, you've got somebody there trying to order a pizza. They're going to go on the app, they're going to go on the website, they're going to place an order. They're going to send a create order request to the order processing service. The order service is going to do some work, and it's going to publish an order confirmed event. The kitchen's going to consume that order confirmed event, because obviously the kitchen now needs to go and create the pizza. It needs to go and make the order. Once it's finished, it's going to publish an order prepared event, which the delivery service is then going to go and consume. everything happening asynchronously, everything happening using events. And of course, the order service is also interested in these events, so that when you're all sat there furiously refreshing your mobile app, trying to work out where your pizza is, you get some updates, you know that it's on its way. So before we get into the observability stuff, I just want to make sure that we level set. Language is a really important thing in our day-to-day lives as humans, even more so when we're dealing with things as complex as software architecture. So what exactly is an event? An event is an immutable fact. An event is something that has happened. It's something that cannot be changed. If you imagine it's the middle of the night, you're in your house, you get up and you need to do something. Maybe you need to go to the bathroom, maybe you just want a snack. So the first thing you're going to do is you're going to hit a light switch. That's going to raise a light switched on event. It is irrefutable at that point that the light has been switched on. You can't unswitched on a light. It has happened, it's in the past. Once you're done doing what you need to do in your house, you're going to hit the light switch again. That's going to raise a light switched off event. The light switched on, the light switched off. These things happen, they cannot be changed. So if that's an event, what exactly does it mean to be event-driven? And I think this gets a little bit conflated sometimes with what I'd call an event-based system. Both event-driven systems and event-based systems trigger functionality using events. The difference with an event-driven system is that they trigger business functionality using business events. Events are not a new thing in software architecture. I started out my career building .NET applications in Windows Forms. I know it's horrible. If you've been there, I'm sorry. We've got this whole PTSD thing together. But in these applications, you could do things when a button was clicked, a mouse hovered, a window was resized. And if you think to the definition of an event, well, there are things that have happened there in the past. They can't be changed. But they're technical events. An event-driven system is using events like this: order placed, pizza boxed, staff member clocked in. You could look at two businesses in the exact same domain, both building event-driven systems, and they'd probably have a different set of events, but they're all going to be clicking buttons. Their mouses are going to be hovering over things. So when you think about events, you'll often hear about this idea of messages as well. Are you doing events or are you doing messages? What is happening in an asynchronous system? And actually, events are simply a type of message. And there's three different types of messages you'll often see. You've got commands, you've got events, and you've got queries. Now, commands and events are very similar. The difference between a command and event is mostly just a statement of intent. Am I asking a system to do something, or am I reacting to something that has happened somewhere else in a system? And then queries, of course, queries are nice and simple. I'm just asking for a specific piece of data. I want some information. So then inside events, you've then got different types of events. You've got notification events, or sometimes known as thin events. These are really small, really lightweight pieces of data that are simply notifying one system that something has happened in another system. And then you've got event-carried state transfer, or what's known as a thicker event. This is where you're carrying the entire state of your entity as part of the event that you send. Whichever type you choose, you've likely got three components in an asynchronous system or an event-driven system. You've got a producer, you've got a consumer, and then you've got some kind of transport in the middle. Here, this is labeled as a bus. This could equally be a topic, a queue, a stream. There's just some kind of transport in the middle. The key difference being the producer and the consumer have no idea that each other exist. One is simply producing events, the other is simply consuming events. The core integration pattern at work is the publish-subscribe pattern. And your producers and consumers have different levels of responsibility in an asynchronous system. As a producer, your main responsibility is to stick to the schema that you agreed on. You agree to stick to a stable and consistent contract. You agree to try and avoid breaking changes where possible to try and keep backwards compatibility for the systems that are consuming your events. But there's things you're not responsible for anymore. And this is where it gets really interesting when compared with synchronous systems. If you imagine you're building a synchronous system, you're making an API call to a HTTP API. you as a developer need to care about the constraints of the system that you're calling. What throughput can that system manage? Where even is that system? What address is it on? Is it responding fast? Is it responding slowly? Is it responding at all? These are all constraints of a system you don't control, but you need to care about. In an asynchronous system, this is no longer your responsibility. You are publishing events, and it is up to the consumer to control and plan for the ingestion rate that they're going to see. It's your responsibility as a consumer to protect yourself. So that's some high-level terminology around event-driven systems and asynchronous systems. Let's now talk a little bit about observability. And it's become a pretty loaded term nowadays. Almost every conversation around observability comes back to this idea of the 3 pillars of observability. Of course, being logs, metrics, and traces. I think this misses the bigger point, though, with observability. These are the what of observability. These are the how of observability. But why exactly do you need a system to be observable? What even is an observable system? If your system's observable, you should be able to ask questions of your system that you didn't know you needed to ask from a place that is external to your system. It's a strange way of putting it, isn't it? Asking questions you didn't know you needed to ask. Let's think about an example. Imagine in your system, you have some kind of outage. Maybe the database goes offline for whatever reason. So you're going to get up, your page is going to go off, you're going to go and fix the database. And for argument's sake, let's imagine the database has run out of disk space. So you're going to go up, you're going to add the disks, you're going to increase the disk space, your system comes back online, happy days. And then hopefully, you're going to put some kind of metric in place. You're going to put something in place to make sure that this doesn't happen again. Once you put that thing in place, the chances of that happening again are obviously much lower because now you're monitoring for it, you're checking for it. The problem with that is complex distributed systems, you're dealing with unknown unknowns. Distributed systems fail in new and novel and different and complex ways all of the time. There is no way you can possibly predict all the possible ways that your system could go wrong. So this ability to ask questions of your system allows you to play detective, to diagnose these things as and when they go wrong. Now that's important in any kind of system, of course. So what is the challenge when you're building asynchronous systems? What's the challenge with observability in an event-driven architecture? So now you're not only dealing with systems that are evolving independently, where you've got lots of these microservices that are all changing and being deployed at different times. You're also now dealing with this asynchronous communication. This, of course, is a type of complexity. And there's different types of complexity you're going to see in your systems. The first type, essential complexity. That's the complexity that's inherent to the domain you're operating in. If you're building a system in the finance industry, in the banking industry, in e-commerce, in pizza restaurants, you've got complexity inherent to your system. It doesn't matter if you use Kubernetes, you use serverless, you use monoliths, you use microservices. It doesn't matter. That complexity is always going to be there. Accidental complexity, though, that's the complexity that comes from the decisions you choose to make as you build your system. I'd argue this architecture, this simple monolithic architecture with a single running process and a single database, has a lower accidental complexity that this complicated mess of microservices does. You shift the complexity into your integration points. You shift your complexity into this understanding cause and effect. Cause and effect is extremely difficult in an event-driven system. Understanding the upstream systems that cause your system to do work and the downstream systems that you have an impact on becomes incredibly difficult. What is it that makes it so difficult? What makes it so challenging to understand this? If you think about making a synchronous API call, you're a developer of the order service, you need to make a call to the kitchen service. It's reasonably easy to infer that you are having an impact on the kitchen service because you're making a call to that address. Frankly, you could follow the bytes across the network and see exactly where that request is going. When you compare that to an event-driven system, though, none of your systems have a direct communication with each other. Services simply publish events, and then they get on with their day. They go and do something else. And consumers consume events, hoping that the people publishing them events care and they don't actually change the schema that they agreed on. This challenge with cause and effect makes distributed tracing the most important part of an event-driven system. Being able to understand how a request flows from system to system to system is vital. And to settle on some terminology again, to get the language right. At the top level here, you've got a trace. A trace follows the complete end-to-end life cycle of a request. Inside a trace, you're going to have lots and lots of spans. Spans can span multiple different back-end systems. Spans can also have tags. And this is where things get really, really powerful. You can add tags to your spans. You can add contextual information about that specific request to your observability. Let's actually see this in action with one of the core perceived benefits of building event-driven systems, evolvability. If you build an event-driven system, you can be evolutionary, you can be evolvable, you can change your system however you want, right? Let's think about this component of the system. You've got the order service publishing the order confirmed event, and the kitchen service is consuming that event. And maybe the kitchen service consumes this event, and actually this is a thin event. This is a really lightweight event. There's no actual data in the order confirmed event. So the kitchen service needs to know what it needs to cook, right? So the kitchen service is going to make a call back. It's going to reach back to the order service and say, actually, can I have some more information? I need to know what I need to make. Seems fine, right? You've got an event being raised, you've got a call back, happy days. But remember, your system's evolutionary, it's evolvable. So maybe another system comes along that's also interested in the order confirmed event. Maybe another 3 come along. Maybe another 1, another 3, and then before you know it, your entire system is on fire. Because all these downstream systems have evolved, have started to consume that order confirmed event, and they're also interested in getting more data. One of the common things you'll hear with event-driven architecture is that services are unaware of the downstream consumers of their events. And whilst this might be technically true, it is a really dangerous statement to make. And this is where distributed tracing can get really powerful. Now you can look at the life cycle of a request. You can look at that initial create order request coming into your system, and you can see the event being published. That's a span. The span is there for the event hitting the event bus. And then you can look downstream from that and say, well, actually, another system has consumed my event, and that has directly led to a call back to my API to get more information. You can now start to understand cause and effect. You can ask the question of your system, for all these GET requests that hit my API, what actually caused that GET request to happen? And maybe it's your front end. Maybe, as in this case, there's an upstream event that you're publishing that is then causing the load back on your system. You can understand what's having an effect on your system. So you can look at this information, and it allows you to make informed decisions about how you develop your system over time. Maybe you look at this and you think, well, we're publishing this thin, lightweight notification event, right? And we're evolvable, right? So we can just change the event payload. We can change that really thin event and start publishing a thicker event. We can start including more data in that initial event. And, well, happy days. People no longer need to call back anymore. And you deploy this new version of the event. You've been evolvable. You've been evolutionary, and now no systems need to call back. You've used your observability data to understand what's causing your system to run and made a change based on that. And now you're all full of confidence, aren't you? You've made this change to your structure of your events, and maybe you need to make another change. Maybe actually now your system needs to start supporting multiple currencies. So currently you're sending the order value as a decimal. Maybe then you think, well, we can just evolve this. We can just change it. We've done it once. We can do it again. So we change that value instead of being a number to send it as an object where you include the currency and the decimal. Does anybody see an issue with this, potentially? Lots of nods. Good. That's good. Because although you might think it's only the kitchen that cares about this event, and the kitchen surely doesn't care about the value, and you're right, they don't. But you're evolutionary. So maybe an analytics service has appeared downstream, and, well, they really, really cared about the value of the order. And now you've just broken a system that you didn't even know existed. Not particularly evolvable, also not a good way to make friends, believe me. So this is one of the challenges you'll get with these thicker events. So what do we do now? How can you deal with this? How can you handle this? And observability is your friend again here. And if there's one thing you take away from this talk, this is it. When you adopt an asynchronous system, an event-driven system, make sure you standardize on the structure of the events that you send, that you publish. This is an example of the cloud event specification. This is a defined specification that determines how you should structure your events. And there's a number of really useful properties in here. You've got the data property. This is the actual payload of the event. This is going to be different for every single event you publish. You've got the data content type. This tells a consumer what type of data is going to be in that data property. Here it's JSON. It might be binary. It might be XML. You've got the time the event was published, and also a uniquely generated ID. This is generated by the producer at the point of publish. This will allow downstream systems to implement things like idempotency, to understand, have I seen this event before? Yes, I have. I can just drop that and get rid of that. And then when it comes to this conversation about evolvability, you've got these top two fields here, the source and the type. The source, of course, tells you as a consumer where this event came from, the production orders system in this case. And then you've got the type, which tells you the type of order. It's an order created event, and really importantly, it is version 1 of the order created event. I'll come back to that in a second. Also included in the specification is specifications for distributed tracing. This is what will allow you to propagate that trace context, to keep that trace running through all of the downstream systems that interact with this event. That really long, complicated string you can see there is a W3C trace context. It's a defined specification for propagating traces. And actually, it's reasonably straightforward. You've got a version at the start. This is the version of the specification. There's only one version at the minute, so of course it starts at 0 because developers. You've got the trace ID. This is that overarching trace ID that this event relates to. And then you've got the span ID, the specific span within that trace that was active when the event was published. And then you've got some flags on the end. This allows you to do things like sampling, to tell a downstream system if the upstream system was sampled. And then you can start to publish this in your events. You can include this trace context in the event that you publish. That will allow your downstream consumers to continue this trace, to understand cause and effect. OpenTelemetry also define a set of conventions. They call them semantic conventions for message-driven systems. I just prefer best practices, but whatever. This defines a set of tags that all spans related to messages to asynchronous systems should have. Things like the name of the operation you're performing. Are you sending a message? Are you receiving a message? Are you processing a message? What system are you using for your messaging? SQS, EventBridge, Kafka. And what is the name of the thing that you're sending to or receiving from? What's the name of the queue? What's the name of the topic? This is all really useful information that will allow you to ask questions of your system. And then I particularly like these two, to include these two things in all the spans for all the messages that you send. The version number of the message that you're publishing, and do the same as a consumer, and also the type of message you're producing and you're consuming. This can then allow you to understand who is using your events. Imagine you're in that same scenario where you need to make a breaking change. So currently today, you're publishing version 1 of the order confirmed event, and you're going to start publishing version 2. And for a period of time, you're going to publish both versions of the same event. And initially, version 2 is going to be really sad because no one really cares about it, but it's going to be there. It's being published. And then you can start to ask the question of your system. Who is using version 1 of the order confirmed event? And hopefully you'll see the kitchen service because you're expecting that. And then you see the analytics service as well, and you can think, well, there's somebody else using my events. There's somebody else dependent on me. And you can, over time, migrate everybody over to version 2 of the event. You can ask these questions of your system to understand the upstream and downstream dependencies. Now, a related topic to observability is how you document your event-driven systems. These schemas of your events are the tightest part of coupling in your system. So how you develop them, how you change them over time is going to affect how evolvable you are. Who here is familiar with the idea of API-first design? Okay, a few hands. The idea of API-first design is that the first thing you do when you start building a new system is design the API. Imagine you've got a front-end team and a back-end team. Before you write a single line of code, you're going to agree that contract. You're going to agree that schema of the API. And then when you come to integrate the two things together, theoretically, they should just mesh together. Now, in an event-driven system, your events are the API of your system. So when you're building an event-driven system, you should really practice event-first design. The first thing you do when you start building a system is design and document your events. And I want to say a really quick word on Event Catalog. This is an open source project by David Boyne, who was speaking earlier today. If you're not familiar with it, it's a way to document and discover event-driven systems. At the minute, you need to load in some kind of specification, an async API document or something similar, and then you can understand how all these events link to each other, what commands trigger what events, what's available. On the roadmap, there are plugins going to be built to actually plug into actual message brokers, into Event Bus, into Kafka. And this will allow you to start building self-documenting event-driven systems. And I think that's a really interesting idea. You've got events flying around. Events have got data. Why can't you just document your system from the actual events? So here, imagine you think that sounds like a great idea. So you start actually logging the contents of your messages into your observability system. Maybe you add them as a tag to your trace as well. So every time you consume or publish a message, you can see the entire contents of the message, which sounds really useful, right? And then if you do that, somebody somewhere in your company, probably a security person, is going to have a minor heart attack. Because, of course, you've just raised the potential to store PII-sensitive information in your observability backend. Probably not something you want to be doing. But there's still an interesting idea here, right? This idea of a self-documenting event-driven system, to have the documentation of your system in your observability backend. So a practice I'm a big fan of is, instead of storing the contents of the event, store the schema of the event in your observability system. Store it in your logs, store it as a tag on your traces. This reduces the risk of you accidentally exposing PII data, but it does allow you to understand the exact structure of the event that you received, of the event that caused your system to do some work. This allows you to play detective, to ask questions of your system, to understand exactly how your system is functioning. The more context you start to add to your spans, the better you can start to ask these questions. Imagine a world where somebody in support in your organization comes to you and says, wow, we've got this customer on the phone, they can't work out where their order is. An ability to go into your system and actually run a query, show me all of the observability data related to order 4567. This is where distributed tracing gets powerful. It's not a silver bullet, though, of course. There's some challenges with this. Here's an example of a full end-to-end distributed trace in your pizza restaurant. Each different color on this trace is a different back-end service. And you can see there's a lot of back-end services here. There's a lot of things going on. And you might initially think, as well as this looking really pretty, it's also pretty cool, right? You can zoom right in. You can actually see the specific message channels that this event passed through. You can zoom into your system and see, well, this event went through an event bus. The event bus was called dev.orders. And then it hit an SQS queue, and it sat in that queue for 117 milliseconds before it was picked up by a Lambda function. You can understand exactly how your system is working. And this is obviously incredibly useful, right? To be able to see the exact transports that a message passed through, but also to understand how long it spent in each individual transport. Now, this is going to require a little bit of work on your end, of course, because you're passing that trace parent as part of the event you publish, but you're going to need to add these spans in the middle. Here's an example of an SQS event. If you're doing Lambda sourced by SQS, this is exactly what you'll receive from SQS. And you'll notice there's this sent timestamp attribute. This tells you what time SQS received this message. You can use that to infer the length of the span, to infer the amount of time that this message spent inside SQS. Now, of course, many observability backends, Datadog included, will automatically generate this information for you. If you're using Datadog on any serverless technologies, you will automatically get this trace propagation through all of these services. But looking at this screenshot again, you can see there's these really two long purple lines in the middle. There's something happening in this trace that takes a disproportionately long amount of time. And this kind of confuses the whole thing, right? You've got this really long that kind of blurs everything you can see. And many of you will be in situations like this. You'll have some kind of long-running business process. You'll have an event that happens, and then there's a bunch of things that need to happen downstream. Some of these processes might take minutes, hours, days, weeks, even. Now, of course, trace propagation is incredibly useful, but it can also cause confusion, particularly if your initial request completes really quickly, and then you've got all this downstream stuff that takes a long time. To take another example, imagine you've got some kind of batch process in your system. At the end of every day, you want to analyze all the order confirmed events from that day. In this scenario, if you were to propagate the trace into your daily job, all the observability from your daily job would be in the upstream traces, which isn't particularly useful. It would also have the effect, if someone was to place an order for a pizza at 10 o'clock in the morning, which sounds like a wonderful thing to have for breakfast, you would have this incredibly long, like 14-hour trace, right? But actually nothing has happened for the vast majority of the time that that trace was happening. So there's an alternate approach here, the idea of span linking. So with span links, instead of propagating the entire trace, you simply store a link in one span that links to another span upstream. This still allows you to keep independent traces. You can keep things independent. You can observe things independently, while still understanding cause and effect, still understanding what caused your system to function. Which can obviously raise the question, well, which is the right one to use? Do I propagate my traces? Do I link my spans? What's the right thing to do? I'm not going to say it depends. The simplest way to think about this is to think about the unit of work. What is the unit of work? What is the business process that's useful to you as a developer? What is it that you want to understand? Maybe inside a domain, inside a service, inside a business process, you propagate the trace because it is useful to you for you to see it in one view. And maybe the upstream system that caused you to function, maybe you link that, you create a link there. So there's no rule, no one size fits all. It really does depend. But think about that unit of work. Think about that business process. Whichever way you do it, this starts to allow you to understand your dependencies. You can look at your system and you can look at, well, my product API has an upstream dependency on the pricing service. I know that because I've got things that are being consumed from the pricing service in my product API. Equally, I can also understand all the downstream dependencies, all the services that are relying on me. You can understand cause and effect. And that adds the required nuance to this statement. Because yes, services are unaware of the downstream consumers of their events. But it certainly helps to understand who's relying on you and who you are relying on. Now, I realize I've talked a lot about tracing there, and tracing gives you an awful lot of value at a micro level, down at individual request. What does that mean for the other pillars? Everyone talks about the 3 pillars, right? And there's a lot of useful things you can still get from metrics, because that micro view is useful, but having a macro view of your entire system can also add a lot of value. So which metrics are important in message-driven systems? And OpenTelemetry also publish a set of semantic conventions for metrics in message-driven systems, best practices, of the things you should care about in an asynchronous system. Queue depth. How many messages are there building up in the queue? If the queue depth is increasing over time, that probably means there's a bottleneck of some kind in your system. Or maybe it's a dead letter queue. Well, it tells you that there's an error somewhere that's sending messages into the dead letter queue. The published and consumed message count, but also the published and consumed message size. This allows you to understand throughput, but can also give you some really useful information if the size of messages suddenly increases or decreases. that can tell you there's been a change somewhere that may have an effect on your system. The message age, how old is the last message that you processed? This can tell you if you're dealing with the throughput fast enough. If you're building a latency-sensitive system, this, combined with the in-flight latency, can also be really useful. How long are my messages spending in the transport that I've chosen? Whether that's Kafka, whether that's SNS, whether that's EventBridge, that can be a useful thing to understand. Of course, errors are always useful. And finally, the event type. How many of a specific type of event have you seen in your system? How many order confirmed events? How many payment failed events? This can be useful for you as a developer, but also useful to the wider business as well. And whichever of these you choose to alert on is going to be really specific to your specific scenario. Do you care about latency? Maybe you care about, you're going to alert on the in-flight latency. Maybe you care about errors, about throughput. The alerts are going to depend on your specific context. Also, success is a really important metric. Imagine your system normally processes 10 messages a second, and then all of a sudden it processes 0 messages a second. There might not be any errors because there's no messages, but that might tell you that there's something wrong. And that QR code there is a link to a really great article by Lee Gilmore on his blog that talks about how Netflix do this and how they do use success as a useful metric. So now that you've got all of that in place, let's actually have a look what this actual debugging flow could look like. Because remember, you're still sat there, your page is still going off, you're trying to work out exactly what's going wrong in your system. So imagine your page has gone off because you've got an increased error count. There's an increased error count inside the kitchen service. So you go and have a look, you head off to your observability backend, and you start to ask questions of your system. Show me all of the traces that have an error. Error is a type of context that you can add to your traces. So now you can see a list of all the traces, all the individual requests that have an error. You can dive into an individual request and look at the individual request that's failing. And because you're doing trace propagation, you can also understand the upstream systems that caused your system to do some work. You can then start to look at what was actually in that event, what was actually in that request that I processed. You can have a look at the schema of that event. And you think, this is odd. I'm sure last week we started putting more information in this event. We stopped it just publishing the product ID, and we started publishing a thicker event. That's interesting, it's changed. So you can grab this exact schema, drop that into your tests, run your test suite, and lo and behold, an upstream system has made a change that has caused your system to fail. You can understand all this. You can ask the questions of your system to understand exactly what is causing it to go wrong. Now, I realize that's a really trivial example there, but I hope what that's shown you is that having this context, having this ability to ask questions is what can help you understand cause and effect in your event-driven system. To understand exactly what has caused your system to execute and who is downstream of you, who is dependent on you. If you always ask yourself the question, how will I know what has caused my code to run? You should always have the observability that you need. Think about this idea of asking questions. Asking questions of your system that you didn't know you needed to ask. Having distributed tracing in place, having context on them traces and the ability to query that context will then allow you to play detective. And finally, think about the things at the micro level, the individual request level. But also don't forget about the bigger picture, the macro view, giving you a high-level look into your system as a whole, and make sure you build this into your day-to-day work. A company I used to work for, we actually used to have in the pull request template, whenever you wanted to make a change, you had to describe how you would know that exact piece of code was in production. It might be a 2-line code change. How would you know that the code you've just shipped has made it to production? If you can always ask them questions, you'll be in a really good place from an observability perspective. Now, today there's been some really, really awesome talks. So I just wanted to do a really, really quick plug for Serverless Days Manchester. If you've enjoyed a lot of the serverless content that's been going on today, we are going to be running a Serverless Days in Manchester in February next year. The CFP is still open if you're interested in speaking. We'd love to have you speaking, whether you're a new speaker, you've been speaking forever. Tickets are also available. There's a whole bunch of other QR codes there for the slides from this talk, my YouTube channel where I've got a whole bunch of other content. And actually, plant-based pizza is a real thing. You can actually go and deploy it and look at it, and that is available on GitHub in that top link. Thank you all for listening. I think I've probably run over time, so if you've got any questions, then I'll be around for the rest of the night. So thank you all.